As we start to talk about, or keep talking about electromagnetism, we're going to talk about inductance, self-inductance, and the energy in an inductor. Inductance. Okay. So we've talked about electromagnetic induction. Hopefully you've read a little about it or know a little about it. Okay. And let's take a look at a neat trick that we can do. Okay. We can move electricity from one place to another using a magnetic field. And it's actually a pretty neat thing we do. You can see we have a big piece of iron there, and we have two coils that are working around it. Okay. We have one on the left-hand side. And you can see it's got a little wire around it, and it's going to have a current that goes through it. I'll try to write on it. Okay. Okay. We're not going to put a current through the other one. But if we keep changing that current, the current that's in there, we can make a magnetic field inside there, no matter what. Okay. And if we use the iron core to kind of keep that magnetic field like tight inside there, we can move it around a little bit. It'll go through here and it'll go to the other side. Well, it's kind of a big so what, unless that magnetic field changes. Because if we can make that magnetic field change, like say would in, for example, in alternating current, where the current isn't constant, where it goes up and down, goes from a high positive value to a high negative value, then the field will shift. It'll get larger and smaller. It'll go from down to up and up to down. That'll make a shift in the other coil. If that makes a shift in the other coil, then any shift will make that magnetic field in the right-hand coil over here turn into an electric current inside that secondary coil. Well, that's a bonus. We want that. If we can get that to happen, now we've moved electric energy from place to place using a magnetic field inside there. And that's pretty cool. Okay, so, and the item we're talking about is a famous item. It is a transformer. Now, like those cool toys, yeah, I'm going to go ahead and talk about it. Okay. This one is called a step-up transformer. Okay. The primary coil is on the left-hand side, and it has 100 to 120 volts in it. And the one on the secondary side has 220 to 240 volts in it. I want to point something out. On the left-hand side, there are 1, 2, 3, 4 coils. And on the secondary side, there are 1, 2, 3, 4, 5, 6, 7, 8 coils. Okay. So I didn't do a very good job of counting them there. Okay. But you can see there are 8 coils. That's not a coincidence. If you want to increase your voltage, you want your secondary coil to have twice as many coils as your primary. That will step up your voltage. Now, what's the cost of that? You're going to decrease your current. Okay, that's how it's going to happen because you can't get more energy out of the system, but you can decrease your current. Okay. Those little wall warts you have in the wall, the ones you plug in so you can turn your Xbox, you turn the power from the wall into power to plug in, say, your USB cable or your Xbox. It does something similar, although it also has a rectifier to help turn it into direct current as well. It's gonna take those sets of coils in ratios that are gonna take it from 120 volts in the wall to 5 volts. That's gonna be nice, play nice with your USB cables, or I think it's 18 volts is what plays nice with your Xbox. I can't remember exactly, but in any case, it's going to change them that way. That's a step down transformer. Okay. That's called mutual inductance. Okay. You've got inducting on one side, electromagnetic induction, and it's going to do some inductance in the other coil. So they're going to be linked together to make what's called mutual inductance. Now, here's a weird thing that is really common, and we use this in all kinds of devices, called self-inductance. Okay. So we had a circuit with a switch and a resistor. Okay. While we have that on, we flip the switch, and the resistor, you can see that one has an internal resistance, that little r, and the big resistor, capital R. We switch it, and it goes on roughly immediately, like almost like with no hesitation. Okay. Well, let's say we took that one and we made really long wires. Well, again, I just stretched it out to be cute, but the point I'm trying to make is that it has really long wires. So in that case, remember, really long wires are going to act like magnets, and they could interfere with other stuff. Okay, but there's a special case of it that we can use that's really kind of interesting, and we're going to look at real specifically, which is the case of if instead of just a real long wire, we replace it with a really, really long wire, a solenoid. So you can see now, instead of a long wire, we have a wire that we've actually coiled to make a solenoid out of. It behaves in a really, really interesting way, in a way that can be useful to us if we want to use it this way. When we close that switch in our circuit, there's the same circuit. Right now, there's no current flowing. We've got our little battery, internal resistance, and a resistance on the outside, and a solenoid, just a coil there. Okay. Okay. Right now, the current's 0, and right at the moment it closes, the current to 0. Okay. Well, the current's going to start to increase, of course, because there's a battery and we've got a closed circuit. Okay. When it starts to increase, the magnetic flux inside the coil will start to increase. I mean, that makes sense, doesn't it? We're going to have a current inside there. The current's going to make a magnetic field inside the coil. And that's going to start to increase. That's a pretty normal thing. I mean, you would expect that. But here's a weird thing. Lenz's law said the coil is going to react, and it's going to induce a current inside itself. Isn't that weird? It's going to induce a current inside itself that opposes the change in flux. So it's going to try to make a current inside itself that opposes that change in flux. Well, if that's an increase in flux, it's going to make a current that makes a decrease in flux. What's the only kind that would do that? An induced current that would go the exact opposite way of the initial current. So we're going to have the current from the battery, and we're going to have a current that goes the exact opposite way. And what does that mean? As the current tries to increase, the change in that current is going to cause that to slow. So it's not going to jump up to that value of E equals big R plus little r. It's going to stop itself. It's going to make it difficult to move. Okay. Now, as it gets closer to the steady state, that change in flux is going to be smaller. There's not going to be much change in current, so the flux will change less. It's going to resist less as it goes. So there's not going to be very much change in that current and not much change in that flux. So there won't be much resisting current. In other words, the current will get, well, the reduction in current will get smaller and smaller. If there's less change in flux, we're going to have less induced current, like I said. And eventually, you'll reach that steady state current, a current that just depends on the resistances and the voltage of the battery. Well, there will be no change in flux then. That solenoid will behave like a little magnet, and there'll be no induced current at all. It's kind of weird, so you may want to rewind back a couple minutes and watch this, look at it again. Now, what does that mean? Let's say we were graphing it. Okay, let's go back to our circuit. Okay, and let's think about what the graph would be like. Okay, that means that the current in the circuit is actually not going to reach the I max value right away. It's not going to reach E equals capital R plus small r right away. It's going to take some time to do that. It's going to make a graph that looks like the graph that I showed on here, where it starts with a current of 0, but it's going to slowly reach that I maximum value, maybe quickly depending on the circuit, but it's going to reach it. It's going to take time to reach it. It's not going to get there right away. And we're going to look at what things make that happen. there's an equation for self-inductance. Okay. The voltage from self-inductance, the voltage that's going to generate that current, sometimes called back EMF. It can be calculated using this equation. Okay. E, and that's the curly E when I write on the board, equals negative L di dt. Okay. So, okay, L is a quantity called self-inductance. It's measured in henries, H. And all that really does is describe the ability of the coil to resist changes in motion. Now, that can be like the number, that can relate to the number of coils it has, how tightly wound they are, like the actual area of the coil, all that kind of stuff is all kind of baked into that calculation of how inductance gets calculated. Okay. But it does depend on the current. The faster the current is changing, the more of this self-induction there's going to be. I want to point out it's negative, which means that it goes against the change in current. If there's a positive change in current, then this voltage is going to be negative. But if the current is decreasing, let's say we open that switch, we're going to get a positive change in, we're going to get a positive voltage. It's actually going to make it go faster. That's like if you've ever opened like a switch, sometimes some items don't go off right away. Sometimes that can be from self-inductance. Okay. Di dt is a change in current as a function of time, just like I talked about. Okay. And a Henry is a volt per amp second. Okay. So volts over amp seconds, not volts over amp time seconds. A volt over an amp second is the unit for a Henry. Many times Henrys are listed in millihenries or microhenries because they can be pretty small. So now that we've talked about what self-inductance is, we have that L variable. We need to talk about how we can define it other than just in terms of the back EMF or the induced EMF that it causes and the change in current over change in time. So we want to talk about it as a physical property. It tells the effectiveness of the inductance coil itself. If the point of the coil is to stop the current from immediately going from 0 to something, then we're going to see how effective it is at doing that. If it takes a long time to get to that current E over R, or if it takes a short time, that's going to be what's described by this L value. Okay. It's a ratio of the flux provided per amp of current. If it puts more flux in there, then any change in that flux will make more EMF. So it'll actually be more effective in slowing down that current from going from 0 to maximum, or from going from maximum back to 0. Larger ratios are going to give you a bigger change in flux, or larger EMF values for equal current changes. So that's why this value is so important. And the way to calculate it is just like it sounds like. It's the ratio of the flux provided per amp. So L is going to be N phi sub B divided by I. You notice I wrote little I because it's a transient current. It's not the steady state current, the current that happens at the end. It's the current that happens between closing the switch and getting to that maximum current. So it's N, because that's the number of loops, times the flux through that loop divided by I. And as long as it's like a solenoid or something like that, where the magnetic field is automatically perpendicular to the area, we can just use the even easier to remember NBA over I, where BA can stand in for the flux because we don't have to do the integral of B dot dA, because we already know that the integral of dA in this case will be A, because B is going to be constant going into the coil or the loop or whatever it is. Now we're talking about the energy. Okay. I was going to say, let's say that we have a bunch of stuff here, like if we were making a graph of power versus time. If we had just our resistor and switch with no solenoid and inductor, we'd have the same power right away. We'd have, what is it, like the voltage times the current, because the current would come on right away, and it would stay constant the entire time. Okay. But but we don't have that. Okay. If we have the solenoid in the inductor, we get a line that looks like that. We get that curved line where it starts out with very little power because there's no current. And over time, we reach the same power rating we would have had with no solenoid and no inductor. Okay. But you can see there's a gap there. I'm going to color that in. Okay. Maybe. Okay. All that stuff over here, let me color it in. All this stuff over here is energy we didn't get. It's energy that wasn't used up in the in heating the resistor. It's energy that appears we lost, but we didn't lose that energy. We actually still have it. If that area is under there, where did it all go? Well, that's actually a pretty easy thing to see if you think about it. Okay, if we look at the inductor or the circuit, the answer is that it all went into the inductor. I mean, that thing is a magnet. Okay, and as we made that magnet have a stronger and stronger pull, that's where the energy went. It's in the poles of that magnet. As the circuit runs through, it's still a magnet. I mean, if we put stuff near it, it would be attracted, or metals would be attracted, or like poles would repel from the ends. So the energy is still in the magnet there. So how does it enter the inductor? Well, it enters it as it goes, as you close the switch, as the current goes from current equals 0 when the switch is open to current reaches a steady state. That's the time that the magnetic field energy goes into the inductor. Is it in the inductor when it's at a steady state? Yes, it is. But you can't get it out. You can't add to it when it's at a steady state because, well, there's no change in flux, so there's no adding to that magnetic field that's inside there. So we can't get any more out of it. And how do you get the energy out? Well, if you open up the switch after it's been running a long time, well, remember you're going to get a positive voltage. A negative change in di dt is going to give us negative times a negative, a positive voltage. That's how we're going to get the energy back out of the inductor. Okay, because it will become unmagnetic over time. It'll become as the current goes down, it'll become unmagnetic, and that magnetic field energy will become electric energy that works inside the circuit. That's how we get all that stuff to come back out of there. Now, of course, there's an equation that we can deduce to come up with how much energy is inside of there. And just like I showed in the graph, the energy is going to come from the power as a function of time. So we're going to actually take the integral of that. So we're going to put in VI times dt. And unfortunately, those quantities are not going to be constants. They're actually going to change as it goes. I'm going to replace V, the voltage, with L di dt. I'm going to leave the I also before I do it, times dt. Now, generally these little operators don't divide out, but these ones are. Okay. When I factor everything down, I get U equals the integral of L I di. Well, that works out pretty nifty. So I can take the integral because the di is the integral of that. Okay, and I end up with 1/2 Li squared, where I is the final current. I guess technically I should have made it small I and taken small I d small I, then from 0 to capital I, and then I would end up with so let me rewrite it. So really it should probably be more like L d I with an I over here with integral from 0 to capital I. that would actually look a little nicer and would end up getting 1/2 Li squared. Okay. If you work out the units, which is not hard to do, you'll find that you get an unit of joules to go with it. Okay. And that's the energy that's in the inductor. So that's the energy that was quote unquote robbed from the resistor as the circuit begins charging.